Hi, everybody. This is Mr. Folly, and welcome to AP Podcast 1.1 for the school year 1920. Can you believe it? What we're going to talk about today is density, states of matter, and mixtures, and be able to see things on a different molecular level. So let's do it. All right. Physical changes. So physical changes are change in mass, shape, but not identity. So the way the mass would change would be if you cut. Whoops. Whoa, looks like it's going on kind of crazy. Change in mass, that would be like if you cut it smaller. So like if I had this and cut it in half, then I would have as much. Okay, it wouldn't change the identity. This would still be clay, right? These would still be voodoo dolls, even if you cut them in half. It would just hurt more. Well, maybe not voodoo dolls, but you get the idea. All right, so cutting, boiling, melting, freezing, molding. Notice they're all the same substance. Okay, and substance is our AP chemistry fancy word for a thing. All right, so this is boiling oil you can pour on people when they attack you. Chemical changes. Change the identity after the change. So, for example, if I start with a living leaf and it dies, it becomes crumbly. It no longer does photosynthesis, the chemicals break down, things like that, and that happens. So if you burn something, it changes the identity. So if I start off with a tree and I end up with ash and smoke, those are definitely new things, and they would have a new formula. Okay, so something burns, dies, precipitates, forms a gas, or changes color. Now, forming a gas, I just have to say this, not boiling. Boiling, remember, is a physical change. So watch out. That's the tricky gotcha question. Okay, and if it changes color, just so you know, not painting or something like painting it. Okay, so if I paint the wall, I coat it with something. I don't change it that way. Okay, a precipitate. This is a precipitate, and again, you don't have to remember anything from sophomore year, but a precipitate is when chunks form out of a solution. So what happened is I mixed water-looking thing number 1 and water-looking thing number 2, and I get a precipitate like that. Okay. Boiling forms a gas, but it is not a chemical change, and that's what I just said there. If I'd have paid closer attention to my slide. Oh, burning. By the way, Nightmare on Elm Street, good horror movie. This poor guy got burned. You don't want to get burned like Freddy Krueger. Pure substances. Elements. Elements are only one type of atom, and they can be diatomic, and you need to know these. The diatomic elements are H, Honkelbrief. Now in the periodic table I gave you, and I gave you it stapled together with other equation sheet things, but Honkelbrief, so there's hydrogen's never alone, never totally alone. So these guys, if I have a sample of fluorine, it's F2. Okay, so it's only one of each type of atom. If I draw a picture of it, like this could be an atom, or this could be an atom. A diatomic element might be like triangle touching triangle. See how they're both triangles, but they're touching? That would be a diatomic element. This would be a monatomic element, just like this is iron, right? This right here could be like oxygen. Okay. Compounds. There's more than one type of atom, and it's not a combination of properties, it is new properties. And they must be bonded, chemically bonded. And on the molecular eye diagrams, they must be touching. So how is a compound different from this? So if this is hydrogen, what would water look like? I think you know water is H2O. So if we said hydrogen was those triangles, let's say this is oxygen. Oxygen is the O. Here's my oxygen, and I would see like little horns on it. Okay, so this would be H2O. Notice they're touching. Because they're touching, that shows they're bonded. Okay, so those would be bonded. If I just had this and I asked the question, and AP Chemistry does ask these questions sometimes, why aren't these two things the same? And you turn into little baby Chucky. This one has the triangles touching the circles. This one, the triangles aren't touching the circles. And believe it or not, that's the right answer. And the touching represents chemical bonding. But really, the state what little baby Chucky sees, and you'll get it right. Mixtures. Any state and any state is possible. States are states of matter, so that's solid, liquid, or gas. Okay. Homogeneous mixture is also called a solution. and every sample is the same. This is the real definition of homogeneous. Every sample is the same. Heterogeneous samples are different. Living things are typically heterogeneous. Now, here's the part that's hard on these. It depends on the scale. I'm going to say magnification. I said scale, but I'm going to write magnification. So for example, you could look at your skin and say my skin is homogeneous. It's a lovely bronze. But then when you look closer and closer, you know that skin is made out of cells, and you've got your little nucleus, you got your little endoplasmic reticulum, you got your little bean looking thing right here, which is the mitochondria, which is the food source of the cell. No, it's not. It's the powerhouse of the cell. You remembered that. I knew you did. Mitochondria, powerhouse of the cell. All right, so what I'm going to do is I'm going to do some tic-tac-toe here for some of these. This is a pure element because it is one type and one type only. This right here is an element because it is one type. Now notice they're different types. This one is a big old circle and this one's a little circle. Now if I told you that this one right here is a mixture, it's a mixture of a diatomic element. This is a diatomic element because of the same thing touching. And this is a compound. I don't know why that line's there, but it is. Okay? And the compound, because it's two different things that are touching, black dot and empty dot touching. It's a compound because two different things are touching. Okay? This right here is a compound. Now I'm going to put the word pure into it. Okay? This is pure because it's only this one type of element. This one is a mixture, which is kind of the opposite of pure for that same kind of thing. So this is a compound. It is a pure compound because there's nothing but that in there. This circle has escaped, and I don't know where it's escaped from, but it has certainly escaped. Okay? How to measure, as they say in Indiana. All instruments have a numbered, an unnumbered, and an estimation. Digital things do too. So see how this says 0.0 grams? That really means that it is somewhere between 0.0 or 0.1. Both of those would be okay. This one right here has two decimal places, so that means it is 0.00 or 0.01. Now if this said 5.00, this scale really doesn't mean that's exactly what it is. It means it's 4.99 to 5.01. So that's an estimation. Okay. On this, if I put a dot right here, this needs to be, it's bigger than 5, right? 5.4 is wrong. 5.41 centimeters is right. Okay? Does that make sense? I know that says millimeters, but that's just a dumb thing. 5.41 centimeters. You need this. The numbered 5, it is certainly more than 5. 0.4, it is certainly closest to 4. Estimation, it's a touch bigger, 5.41. Now if someone said it's 5.42, say Sammy said it's 5.42, do I go, get out of here, you have no place in this class, you fool? No, you can see how they'd say that, right? That's reasonable. So that estimation is reasonable uncertainty. Now if I said it was 5.49, if Alyssa said it was 5.49. Gee, I even did that on purpose. I didn't. You'd say, no, that's just wrong. That's wrong. That's just wrong. I can't take that. All right. Separation by distillation. Okay. This is separation by boiling point. So what happens is I start off with a solution that has water molecules and it has, let's say, sugar. And I'll make sugar be a squiggly today. Water molecules, squiggly. Water molecules, and then another squiggly. Okay, so what happens is when we heat these up, the water will, something's going to boil away first. So what happens is the water boils away first, and then we collect it. The sugar doesn't boil away. So that means I'm left with, in the end, all I have down here is my sugar particles, and over here in a separate beaker is my water. Okay? Make sense? I hope. So that's one way to separate a mixture. Density is love. Oops, I gotta tell you why. So if you remember, density is mass over volume. See how it looks like a heart? Aww, with a knife through it. Okay? So it is a ratio of mass over volume. Okay, be careful. Sometimes when you say something is heavier, we mean it's more massive. So just be careful with that. Let's go to some applications. More dense things sink. Okay, Saturn's density is 0.687 grams per centimeter cubed. Remember, it's a gas giant, so that means it's mostly a gas. Water's density is 1 gram per centimeter cubed, so that means Saturn would float on water. Isn't that crazy? But we don't have enough water to float Saturn, but that's it. All right, separation by filtration. So notice a lot of these things are separating solutions, which are typically water-based. Now they don't need to be water-based. They could be something else that you're unfamiliar with. It could be like benzene, which is a liquid, and things dissolve in that. It could be alcohol, which is a liquid, and things dissolve in that. But filtration is simply separation by particle size. I love this picture. AP Chemistry will ask you to describe this picture, and again, you've got to get used to, you do not need to know the words permeate or retentate, although they're fun to say. If I said explain the process of filtration using this picture, you would little baby Chucky it. There's holes in the bottom of it, and the little ones can fit through the holes, and they end up down here, and there's some parts down here, but the big ones, they're too big to fit in the hole, so they're left over. That's it. You literally say that. Pictures and AP Chemistry and AP Biology and AP Physics should make you think little baby Chucky and just describe what you see. All right, separation by chromatography. We're going to do a Kool-Aid chromatography lab next day or so. So we're going to separate by polarity and size. Now you don't need to know what polarity is yet. If you do, that's wonderful. Size, you should know what that is, bigger things and smaller things. Two types of substances, polar and nonpolar. That's what you need to know about polarity. Polar has charges and will stay with other polar things. So polar and polar, they're buds. Okay. Polar paper means that the polar parts move slower. So if I'm right here and I love the paper and I've got a solution, so the solution is flowing up. The solution is being pulled up by capillary action. And I'm right here and I love this paper, I'm not moving very far. Okay? But if I don't love the paper and I love the solvent, I'm going to move up and I'm going to be up here. At least part of me is. Okay? So what happens is you get one area with a dye zone. Now you could have other ones, and it will be elongated like this, and they will probably be different colors. I'm colorblind, so I wouldn't know. Okay, so on this same setup, you would then be able to tell that this guy right here is most attracted to paper. Not paper. I didn't write that. Most attracted to the solvent, which is typically water. And this one right here would be less attracted to solvent. And if it's right here, this would have no love for solvent. Okay, that's it. And if you look at it, I think if you little baby Chucky'd this, which one gets caught up in the wave more? Well, this one goes far with the wave, this one hardly goes with the wave, this one doesn't go at all. And little baby Chucky can do that too with chromatography. Review. Woohoo! Physical changes stays the same thing. Chemical changes change the identity and physical properties. You should know distillation, chromatography, and filtration. And know that elements, compounds, and mixtures by picture, touching is a bond, and little baby Chucky is a genius. Woohoo! How do I end this? I swear it's over. There it is. Toodles.